So we're trying to do some new things to get the captions going. Hopefully this will be an improvement over Monday. But we'll see. Let's see. Oh, hi, Ming-Chi. Sorry, my pronunciation apparently isn't good enough for the captions to spell your name right. Hi, Anna. Hi, Rain.
Hi, good morning.
Good morning.
Hi, good morning.
Good morning, Anna. So we're trying a slightly different setup today, so that we have the closed captions, which you should be able to see right now. Brown asked us to do this to help. Basically, for a lot of people, it would be helpful if the closed captions work well. So please let me know if something's not going right today versus what you expect. And remember what we talked about last time was it's really helpful if people ask questions as I'm speaking in the chat box, and it would be really good if other students respond to that question to those questions as well. I don't think that it's too distracting to have something going on in the chat window at the same time as I'm talking, and I will be able to respond to it when I notice what's happening, if that makes sense to everybody. So does everybody know how to post a chat comment? You go down to the bottom, like, oops. See if I can get it to do it. You go to the chat up here. Then you type your question. Does that make sense to everybody? Why don't you type in something to the chat window now? Okay, great. So let's start. Last time we dropped off. We started out talking about basically the velocity field in a turbulent flow, and then we started to touch on tracers and what those might indicate about the flow patterns. So as you might recall, we talked about the straining and shear and confluence and diffluence, and we're going to get to that later in greater detail. But this is just part of the thinking that we have right now about how we might describe a flow field simply. This is a lot like when we did the Helmholtz decomposition stuff that we talked about in Vallis to separate the divergent part being purely ageostrophic velocity and the rotational part being purely geostrophic velocity. So those pieces of the story are coming into greater fruition as we continue. We're going to be pinging back and forth between what sets up different patterns of flow field and what can advect and what can converge and what can diverge and what confluence and diffluence mean and all that stuff, shear and strain. But one piece that we haven't talked about, so this gets us into the rotating turbulence aspect and setting up the groundwork for that. But what we haven't talked about is the stratified turbulence aspect. And so, as we know, both the ocean and atmosphere are stratified fluids. We've been talking about that and the hydrostatic balance being one important on large scales or small aspect ratio being one really important aspect of the stratified flow, the stratified nature of the flow. So let's talk a little bit about the ocean mix layer from observations. We're actually going to talk a lot about observations today. So this is a nice place to start. So this is data from the Ocean Climate Station, PAPA, and that is in the middle of the Pacific Ocean. And now it's actually a permanent mooring. It looks kind of like this. And it's at 50 north, 145 west in deep water, about 4 kilometers. So this is kind of a typical mid-Pacific location. And it's in fact so important for weather forecasting in the United States that before we had the technology to put a mooring out, they used to have a Coast Guard ship maintain its position there at all times. And so this is one of the longest records we have anywhere in the world, because first it was Coast Guard ships and then it became a permanent mooring. One of the nice things about that is having this continuous measurement. So beneath this buoy, there's a chain of thermistors which detect temperature changes, but also conductivity temperature sensors which detect salinity changes. So you can make a map, overlay the different changes throughout the seasons, like is shown here. So, and sometimes it's called OWS. That's the old name, Ocean Weather Station, and sometimes it's called OCS, which is Ocean Climate Station. So, as you can see here, in April 1st, so right at the end of the winter, this location, there's very little mixed layer. But deep down below about 100 meters, there's a stratification, which is going towards colder temperature at deeper water. And that a little bit earlier in the season, in January or December, there was still a mixed layer, which was about 100 meters deep. And so what we're seeing is, and then in the summertime, there's a very shallow, very warm mixed layer. So as we go August, October, December, January, April, August, you can see that there's a cycle of the appearance of a warm mixed layer and then the disappearance as the conditions change. So basically, if the atmosphere is warmer than the ocean, you tend to have a warm mixed layer, which is relatively similar to the atmospheric temperature, but in the colder seasons, that the ocean is releasing its heat to the atmosphere, driving convection, and eventually you see these other profiles. Down deep, down below this seasonal mix layer, we see that there's a pycnocline or a thermocline. So pycnocline is an increasing density layer, or thermocline is a decreasing temperature layer. Cline means increase or decrease, a change, and pycno means density. Thermo means temperature. So you can see the stratification below down here is relatively insensitive to the seasonality, but the mixed layer is highly seasonal. So as we think about processes that are involved in the mixed layer, mixing the mixed layer, waves, turbulence, convection is part of the game. We talked a little bit about Kelvin Helmholtz before. I wanted to show this movie of Kelvin Helmholtz. So this is a Kelvin Helmholtz instability in between two fluids of equal density. And you can see how the turbulence is wrapping up the layer and homogenizing in between the two different temperature densities like this. But you can see that there's still an awful lot of very complicated fractal-like structure inside these little pieces. This is actually done using an adaptive refinement mesh simulation. This is a video that I found put up on YouTube by Kevin Schall. And this is actually, I believe this is a 2-dimensional simulation, but you could have done the same thing in 3D. But you can see another consequence of stratification is not a turbulent consequence, but it's actually, there's a different kind of waves that are present in a stratified fluid, internal waves. There's a missing letter there. That should say strange, not strange. strange perpendicularity of internal waves. So internal waves are gravity waves, like surface gravity waves, the one we talked about last time, but they ride on the density interfaces within the fluid. And they have the very peculiar property that their phase velocity is perpendicular to their group velocity. So their phase speed is perpendicular to the group velocity. And what that means is that you get these funny beam-like structures in a uniform stratification penetrating away from an initial source. So I have a movie here that maybe makes this a little bit more clear. In this case, there's a paddle in a tank, and this is the vertical direction shown in the vertical here, and then the horizontal tank direction. And you can see as these waves propagate, let's start that again. You can see that the phases, the crests and troughs of the waves, shown here in the different colors, this is an impulsive forcing rather than a periodic forcing. And you can see now there are lots of different beams superimposed. They still have this kind of funny perpendicularity about the way that the packets and phases are propagating. So when we have a stratified fluid, we're going to have these kind of waves superimposed on top of the turbulence. And generally, the way to think about it is that for small amplitude disturbances, the variability will be dominated by a wave-like response. These waves aren't overturning or breaking necessarily, but for a large amplitude variability, these waves could break and drive turbulence. Or if we have really strong variability, such as in the mixed layer, we're just going to have overturning turbulence and not too much of a wave response. So we'll have to think a little bit about this. And so we come into thinking a little bit about the energy that's in the kinds of turbulence. We talked last time about Joule's experiment, which relates the internal energy produced by turbulence. But I said then that actually that's not the important kind of energy for a Boussinesque fluid, because the conversion between internal energy and mechanical energy requires compressibility. Our biggest exchange of energy is going to be between the potential energy and the kinetic energy. So let's think, when we go back to our mixed layer case, what the potential energy is like. So here in August, we've got a lot of warm, light fluid sitting on top of colder, dense fluid. If we were to mix that up, say, and try and get us to the April case, I should go chronologically, get to the October case, you can see that this warm fluid here has been mixed with some of the colder fluid from over here to make the October profile be in the middle between a deeper mixed layer, but somewhere in the middle in temperature between the August surface mixed layer and the August picnic line. So the interesting thing about that is that actually raises the center of mass of the fluid. In order to get to this intermediate temperature, you have taken denser stuff from this part of the August profile and mixed it together with lighter stuff, and that makes the average temperature somewhere in the middle, but it makes the center of mass higher. So we're lifting we're lifting dense fluid and pushing down light fluid in that mixing process, which means mixing of the mix layer increases the potential energy of the layer. Now, if we could somehow magically sort this fluid back into, say, take all of the lightest ones and put them back, let them settle toward the top, and all of the densest ones and let them settle toward the bottom, then we could re-stratify the layer. And so one of the key concepts that we want to think about is a potential energy cycle, which is balanced between things that might mix the mixed layer, increasing the level of potential energy, and things that might re-stratify the mixed layer, which is actually making it less mixed, making it unmixed, but putting by putting light stuff on top of dense stuff. And as we get into the submesoscale, we're going to see that submesoscale variability actually has the characteristic of restratifying the mixed layer by extracting potential energy, whereas small scale turbulence, like the Kelvin-Helmholtz turbulence, tends to mix and increase the potential energy of the layer. So as we start thinking about the energy cycle, this is going to be important. Okay. So Thorpe Chapter 2 really focuses on the measurement of open ocean turbulence. And so I'm going to skim through some of the topics that Thorpe discusses and talk a little bit more about a few more modern instruments than the ones that Thorpe describes. So obviously we've already been talking about temperature and salinity, so you might think, how do you measure temperature and salinity? Well, like I said, you get something called a CTD, which measures the conductivity using or salinity is related to the conductivity, the temperature, which is a thermos, and then this instrument also measures pressure through having a compressible element that returns an electrical charge to record the pressure. If you put those things together, you can measure the salinity, the temperature, and the depth. So this is one that's called a fast CTD. And it is so fast, in fact, that you can tow it up and down quickly from a ship, this is a set of observations from the Mesobob experiment that Akash was actually on one of the ships. Leah, and from my group, was also on one of the ships. And this is the kind of measurements you can see. So this is showing two different profiles of temperature, two different profiles of salinity, two different profiles of density, which is the combination of these two plus the pressure part. And you can see the kinds of detailed structure. This is so fast, in fact, that you can take the vertical derivative to get the stratification in temperature and see all of these interesting interleaving layers of relatively higher stratification. This is all in the upper ocean, so this is really mixed layer processes that we're seeing as detected with a fast CTD. Now, what do you put a fast CTD or a CTD on? You could put it on a glider, which is something like this. So this has wings and it changes its buoyancy. This sea glider, this is one example of the glider, and it swims up and down. In the Mesobob experiment, the sea glider actually took a trajectory like this. This is Sri Lanka and India. And this is what the profiles that come out of that look like. You can see there's a mixed layer. This is temperature on the top and salinity on the bottom. You can see a mixed layer, that thermocline below, and then in salinity you can see bursts of fresh and salty water within the mixed layer. So there's horizontal variability, and then also a halocline, and you put the thermocline and the halocline together and you get the pycnocline. So there's a lot of interesting structure that can be seen in temperature and salinity like this. Of course, you might also want to measure the velocity. Measuring the velocity directly with like a current meter is pretty hard to do because the turbulence that we're thinking about is very small. So instead, oceanographers have been heading towards using acoustic measurements of velocity. So typically a Doppler measurement. So that means that if you ping a sound wave against something that's in the fluid, and if that thing that's in the fluid, whether it's just a change in the density or maybe even phytoplankton or something like that, a scatterer they're called, when you get the reflection back from that, if that scatterer was moving toward you, you get a higher frequency, and if it was moving away from you, you get a lower frequency than the broadcast frequency. So if you use multiple beams, you can see what these look like, multi-beam ADCP. You could put it on a mooring, you could put it on a bottom mount, you could put it on an AUV like a glider, or you could put it on a ship. You get a profile of the velocity in the direction perpendicular to the beam of these sound waves. If you do multi-beam like this, then on large scale features, you're actually able to get multiple components of the velocity. For the features that are bigger than the scale of the beam spread. if you really want to get all three velocities, you can't do it over a profile like this, but you could do it at one point. So there's a similar instrument called an ADV, for acoustic Doppler velocimeter, that focuses multiple beams all on one little sample size. And so in this case, you can actually get three components of velocity at the same point with high accuracy. And if you have a series of these instruments, you can get a time series from one instrument, but you could actually have an array of them and get a kind of map of the field. So Katie McCaffrey, who was a grad student in my lab in Colorado, wrote this nice paper, and this is an example of the U velocity, V velocity, and W velocity from a bottom-mounted ADV that was put into place by Jim Thompson in a tidal estuary off of Puget Sound. And so you can see that while there is low-frequency tides, this is time in days down here, you can see all this interesting turbulent structure in high-frequency stuff, and you're getting all three components of the velocity from this kind of an instrument. This was a set of observations with just one instrument, but you actually could do it with multiple if you had enough money. And another way that you might measure velocity is with something like this, a Lagrangian instrument. So this is out of Eric DeSaro's, this instrument was developed by Eric DeSaro's group at the University of Washington. And it goes up and down, riding on top of turbulent structures in the mixed layer. So as they are overturning the mixed layer under the effects of things like wind and waves, so this was an experiment with a floating bridge to contrast how much waves have to do with the mixing of the upper ocean. This little probe rides up and down along with the turbulence, profiling and measuring the large-scale vertical velocity by following the fluid. And using that, you can compare that versus observations or scaling laws for what you think the large-scale vertical velocity should do as a function of wind stress. But of course, what we really are interested in, if we want to think about the effects of turbulence, is something like an eddy diffusivity or an eddy viscosity, or really just the fluxes. So if we were thinking of a diffusion of temperature, we might have a diffusivity, kappa, and the flux of temperature, that is the transport of temperature by diffusion, would be minus that diffusivity times the gradient of the temperature. And here we're using the vertical direction because we're think about this in the presence of stratification, like in the mixed layer. Why won't this go away? Try that again. And of course, if this is an eddy diffusivity, this is really an approximation to the covariance of vertical velocity and temperature anomaly. This is really the turbulent quantity that we would be after measuring if we could. In order to measure this, though, look, you have to have a velocity measurement co-located with a temperature measurement. And as you might remember from the instruments we just looked at, the CTD is how we measure the temperature, but the acoustic sensor is how we measure the velocity. And if you put a CTD inside of the acoustic sensor, these things are you're going to interrupt the flow that's causing the temperature. So this is a bit of a fiddly measurement to make. There's a lot of inferences about the size and the co-alignment that you could have to measure such a flux. This is also done in the atmosphere with what's called a flux tower, which we'll talk about when we get next week. So temperature is actually not a conserved quantity. It's really the heat that's conserved. But in a Boussinesq fluid, it's easy to get from the temperature to the heat by just multiplying by the density and the specific heat capacity. So we can convert the temperature fluxes into heat fluxes by just multiplying by rho naught Cp. And what we might want to do with that ADV, where we have all three components of velocity, is we might want to look at the velocity transported by turbulence, or the momentum transported by turbulence. And instead of a flux, we call that a stress. So a stress is a covariance of, so this is the Reynolds stress in the one component of the 9 components in the Reynolds stress, the W prime, U prime cross correlation or covariance. And so an eddy viscosity would approximate this with a gradient in the mean velocity field and a viscosity. Of course, there's a real molecular viscosity and diffusivity, which also looks something like this. But those are typically much, much smaller than the turbulent viscosity or turbulent diffusivity, which is just a crude approximation to these real fluxes. One of the most important fluxes to think about, as we already talked about in the potential energy case, is the flux of buoyancy, or which is sometimes called the buoyancy production. We'll get to that in a minute. But that's the WB covariance, or if you want to think about what B, the buoyancy is, it's really the density anomaly scaled by the background density in a Boussinesq fluid multiplied by the gravity. So this has the units of acceleration times velocity, and it's negative buoyancy. So, but what this thing tells you is if things that are buoyant tend to be moving upward, or things that are dense tend to be moving downward, this is a positive number. So when we are extracting potential energy, this number is positive. When we are injecting potential energy through mixing, this thing is negative. So stresses and fluxes can be measured with an ADV or simultaneous temperature and velocity measurements. Or we could use something like a bulk formula or a eddy viscosity or eddy diffusivity, which is an estimate of those stresses and fluxes, but it's just an approximation. Another thing we might really want to measure, thinking about our Kolmogorov-Kraknin theory, are the dissipation of energy or vorticity or entropy. And that's something that we can measure using an ADV. We actually could calculate, well, we need 2 ADVs because we need gradients in space of velocities. So the dissipation is the strain rate double dotted into itself. So the strain is a second-rank tensor. So if I want to get a scalar out of the second-rank tensor, I have to dot this in both directions. So this is with Einstein summation implied. So I'm going to sum over all 3 components of I, sum over all 3 components of J. And if we write out what the strain rate tensor is, it's this object. It's the symmetrized velocity gradient. So dui dxj plus duj dxi. So this is symmetric because it's been symmetrized. We added the 2 swapped components together. So if I swap them again, I get the same answer. And then we're summing over I, j, 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 I across this full product. So this is, if we were to write down the momentum equation and figure out how much dissipation of energy there was, this would be the term that comes out in general. This is extremely hard to measure. So more often, like if we had 2 ADVs, we would set them up separate in the vertical, or an ADCP profile. We could also estimate just du dz. So just one component of this. But if the flow is isotropic, the turbulence is isotropic. That means if different directions are all behaving the same way, then just one component of the shear would actually be representative of this whole system, which has all the different directions represented. And so in that case, this dissipation measurement can be approximately simplified to this simpler formula. In practice, we also could use the scaling of, the Kolmogorov spectrum, where its magnitude is proportional to epsilon to the 2/3 times wave number to the minus 5/3. We could use that to estimate epsilon just from having measurements of the power spectrum. not even trying to measure these small scale viscous scales that are implied by these two explicit formulae. So there are a lot of things. The reason why we care about the dissipation is because the dissipation is the dissipation of turbulent kinetic energy. And we're going to talk about how that goes in just a second. The last thing that we want to talk about as being an important quantity to measure is the temperature variance dissipation rate. So this is the same game as the dissipation of kinetic energy, but the dissipation instead is of the temperature variance, or the which is proportional to the potential energy. The temperature variance is or the potential energy anomaly. This is something very similar, except it's not a second-rank tensor. It's just the gradient of temperature dotted into itself. So we have an x gradient, a y gradient, a z gradient dotted into itself. Or again, we could assume isotropy and get something that's similar to the formulas that we just had. We could measure both of these things together at the same time using something like slowly through the water column, recording data as it goes. And there are all these little probes, tiny little things that are designed to measure these small gradients in temperature and small gradients in shear or velocity in different directions, so as to measure the epsilon and chi as it falls. Chi being this temperature variance dissipation rate. It's very difficult to do this in a permanent mooring sense, but some new things called chi pods are actually developed to be high-speed thermistors that can measure the thermal variance dissipation rate even on a permanent mooring or a semi-permanent thing, rather than in this dropping feature. This is starting to give us a better sense of how these temperature variance and velocity variance or energy dissipation vary through the seasons, so that we can understand better how mixing is related to the formation and restratification of the mixed layer. Okay, so before I move on, are there any questions? Been going for a while. Let me go see what's in the chat box. So Mingxi has asked about the relative velocity between the scatterers and the seawater. Typically, the things that are the important scatterers are either small phytoplankton or actually gradients in the sound speed itself. So the assumption is that the motion of the scatterers, at least on average, is reflecting the motion of the fluid. So we don't tend to have a relative velocity between the two. And that, obviously, if you're detecting at other wavelengths, which might be reflective of very large things like fish, that might be a bad assumption. So it depends a little bit on the frequency that you're using for the ADCP or ADV as to what you get. Any other questions? Okay, great. Let's continue a little bit more, and then I'll stop and we can have a discussion at, say, in about 5 more minutes. Okay. So you might have gotten the sense already that this is a pretty intensely statistical field, the study of turbulence, because there are all these crazy little structures. And so we can't really measure them in great detail. We can't show all of those complicated eddies and overturning and all that kind of thing. So instead, what we do is we sample from them statistically with these instruments, and then we think about what those statistics mean for the size and scale of the structures. These are some of the figures from papers from our group showing some of the statistical approaches with the with the citations down below. This upper left-hand figure is a probability density function. So it's the probability of finding changes in velocity over the RMS of those changes. So what we're looking for here is the shape of velocity anomalies in time. And the dashed line here is showing a Gaussian distribution. This is a semi-log axis, so it's log in the vertical, linear on the bottom, which means that a Gaussian in this appears as a parabola, and you can see that for the smallest velocity perturbations, you actually do see a pretty Gaussian distribution. But for the larger amplitude anomalies, the things that might be coherent turbulent structures, we see a much flatter distribution than Gaussian. So it's an approximately exponential tail. That's one of the characteristics of strongly turbulent coherent structures. And it's true, it's showing all three components of velocity here. And it's kind of interesting to think why the U and W components are more intermittent than the V component, which has to do with the direction of the flow versus the cross current direction and the kind of orientation of the overturning structures. There's a lot to learn from this kind of a statistical look at what the structures are doing. Similarly, we could have, instead of thinking of the probability of different jumps over time, we could have tried to measure the autocorrelation. So this is the correlation of a velocity measurement with itself at a later time, on average over a long time series of different measurements. So when this time difference between them is small, you're basically saying how correlated is something with itself. So we expect the autocorrelation function to start at 1, which is something that's correlated with itself. But as the separation timescale between two different measurements gets bigger, it drops off like this. And so you can see all these individual measurements in the spaghetti, and then the mean over all of them is this black line, which tells you that in this particular location, in this particular velocity direction, the turbulence has a time scale of about 10 seconds or so. But there are still some structures which actually are persistent, maybe out to 200 seconds or so. So this is another way of describing the coherence of the turbulence. The structure function and the power spectrum. So the power spectrum we've already talked about. This is the amount of energy per unit wave number as a function of the wave number. And we saw, this is actually for submesoscale features showing here. So the slopes are pretty steep. Here's the two-dimensional turbulence slope of -3. And here's a -2 slope down here. And you can see that in this particular model and observation, so there's ADCP observations of the submesoscale and modeled submesoscales. They're somewhere in between the -3 and the -2 slopes. They're rolling off a little slower, so they're somewhere in between the Kolmogorov -5/3 and the Kraknin -3 limit. That's another way of processing turbulence measurements or turbulence models, comparing. And then the structure function, which I will describe in more detail on the next slide, is the difference between a measurement of velocity or temperature or some other measurement at two different locations. And in this case, you're looking at the difference to some raised to some power. This is the second order structure function, and again, it's a models in green. But actually, both of these are models, but one is a model of drifter velocities. That's the one in green, and one is the model at a grid point, which is the blue. So this is a comparison between the Eulerian and Lagrangian structure function. This is from Jenna's paper, which you can go and find at this location. Actually, it's her other paper, but this is... and so in this case, it's the separation distance that is the key independent variable. And so there's a relationship between the scaling of these structure functions and the power spectrum. It's kind of similar information between these sort of statistical measures. One of the most important things we can think about when we try to interpret those kinds of statistics is whether we can assume that the turbulence is stationary, that is unchanging in time, homogeneous, that is unchanging in space, or isotropic, that is all different angles are behaving in the same way. And what I mean more specifically about that is, let's take the specific example of the structure function. And so, like I said, the structure function is a measurement. Here I'm writing it for temperature, but it could have also been a velocity component. At one location, minus at location x at time t. And this temperature is located at x plus some separation r. Both x and r are vectors here. At a later time, t plus tau. This then is raised to the second power. So we're looking at and then averaged. So we're looking at the variance of this temperature at one location, temperature at another location, temperature one time, temperature another time. So it's a difference, 2-point statistic, 2 points in space and time are being compared. If they had the same temperature, this would be 0. If they had really different temperatures, this would eventually go to just being the variance at one location plus the variance at the other location. So if they're correlated to each other, the structure function is small. If they are uncorrelated, the structure function is large. So that's the nature of this. At small scales, small separation scales, the correlation is higher, the structure function is lower. At large scales, the correlation is lower, the structure function is higher, and in fact it levels off and becomes independent of scale once your two measurements are far enough apart from each other. So that's the structure function of temperature. And in general, we can see, look, it depends on the vector x, it depends on the vector r, it depends on the time, the initial time t, and it depends on the distance in time tau. So it's really this high dimensional object. It depends on x and it should be r there. X and r and t and tau. So if it was stationary, what we mean by stationary is that this statistic, this structure function, doesn't change in time. It might still depend on the separation time between the two locations, but it doesn't depend on which starting time you start at. So instead of being depending on all four, if it's stationary, we can drop its dependence on t. If it's homogeneous, then it doesn't depend on this separation. It doesn't depend on the initial location x. It just depends on the separation r. So in that case, if it's homogeneous and stationary, then it just depends on r and tau, not x or t. If it is isotropic and all angles are the same, then it doesn't depend on the vector r, it just depends on the magnitude of r. So the point is this statistic might depend on all of the independent variables that go into it, but if the turbulence is stationary, homogeneous, and isotropic, it only depends on the magnitude of the separation and the time scale of the separation. It doesn't have to be a structure function to make these kind of things. We could also have made the same kind of assumptions about any of the other statistics that were differences. So we could have thought about it in terms of the PDFs, we could have thought about it in terms of the autocorrelation, we could have thought about it in terms of the power spectrum. And this is a nice figure from Haijing's paper, recent paper that's linked down here, estimating the stationarity of that power spectrum that we showed here. Here's the stationarity estimation, and the way that he estimated that was he compared the power spectrum you get with different starting times over a series of days, and you can see that there's some uncertainty at the largest length scales, which are still apparently evolving on those time scales, but the small scale structures are not so different. So this is a relatively stationary field, at least for wave numbers that are large. Homogeneity, he estimated the effects of inhomogeneous or heterogeneous flow aspects by comparing the power spectrum from different subdomains within the whole domain. And you can see that that actually does induce some uncertainty in the power spectra all the way down from across the whole range of scales that are able to be estimated within each of the subdomain boxes. We can't actually estimate these lowest wave numbers because the lowest wave numbers are actually bigger than these boxes that are in the subdomain boxes. You have to have the longer length scales of the whole domain in order to estimate those. But these two figures together give you some sense of how heterogeneous or non-stationary the flow is, and it looks like heterogeneity is actually a bigger issue in this flow than stationarity, at least for the wave numbers above about 4 times 10 to the minus 3 in cycles per kilometer. And then isotropy, Haijing did the same thing where he, instead of breaking up into boxes like this and doing the two-dimensional power spectrum, he looked at the power spectra in different angles across and around and around and around in different directions. And so now the uncertainty here is due to looking at different directions one at a time and then making an envelope of the different directions. So that's the concept of stationarity, homogeneity, and isotropy, and which is frequently assumed. But if you have really good measurements or you have a three-dimensional model, you can actually test whether those the last thing I want to say before we pause is you can do these kind of measurements from lots of different instrument platforms. You can do it from a ship, you can do it from a buoy, you can do it from a platform, you can do it from a flux tower, you can do it from a autonomous sailboat called the sail drone. You can do it from a glider, you can do it from a Lagrangian instrument, you can do it from a vertically profiling thing called a wire walker that crawls itself up and down underneath a mooring. This is one of the coolest things about modern oceanography, is that all of these platforms are getting smarter and smarter, even though the instruments are relatively similar to what we've been using for some decades. So by exploiting different platforms, we actually are getting a better and better sense of what the spatiotemporal variability of the turbulence looks like. So with our few remaining minutes, why don't we switch over and see if there are any more questions? You feel free to unmute at this point. I'm happy to, we can chat or text. Either one works. Yes. So Jihai is asking how big the error bar is from this figure from Haijing's paper. Yes, that's exactly what the error bar is showing. It's showing how different the different directions are. So if the flow were really anisotropic, that is not isotropic, then the error bars would be really big. The fact that it's relatively tightly constrained, all these different directions are all agreeing, is telling you that actually the flow is pretty isotropic. It's also pretty homogeneous. It's maybe a little more homogeneous than it is isotropic, which is a little bit dangerous because there are more angles here than there are subdomains here. You have to pay attention to how many samples. This is a sample-dependent statistic. But for sure, looking at stationarity is not the issue. It's really, really stationary. The homogeneity and isotropy are a bigger problem. All right, any other questions? Okay, so for Friday, we're going, remember the homework is coming due. We definitely have covered all the aspects you needed to have to get to the homework. We're going to discuss more of Thorpe, Chapter 3 of Thorpe, which is going to start us into the conversation about energy budgets, more than we've gone so far. And in addition, we're going to have any questions about the homework. So maybe the best thing to think about is if you could send me an email by early Friday morning, late Thursday night. I can prepare some responses to questions. That's probably the best thing to do for this setup. And keep reading the book. And then next week we're going to switch over to Wingard. And the homework will be drawn from both Thorpe and Wingard. And I will pick chapters and subsections of Wingard by Friday. So you'll have a sense of it to know which sections are reading. And as we said before, there's a lot of overlap between Wingard and Thorpe. Thorpe is a little bit more words and a little less equations than Wingard. So that's why we started with Thorpe. But we're going to be able to contrast the atmosphere and the ocean through the comparison of the two. Okay. Thanks very much, everybody. Take care, stay safe, wash your hands, all that stuff. We will see you again on Friday, and we'll have another class.
Thanks, Taylor.
Yeah. Bye-bye, everybody.